Hello APC Mechanics students in Unit 1 Kinematics, Class 14 Motion in 2 Dimensions, Part 2. Then Section 1, Period Frequency and Angular Frequency. For a repetitive motion, we can always define the following quantities: period frequency, angular frequency. And whenever we're talking about repetitive motion, one perfect example is circular motion, because as the particle is moving along a circle, the motion will repeat itself due to the symmetry of the trajectory itself. The frequency denoted by small f, its unit is hertz, is the number of cycles per second. The period, which is the capital T, and its unit is s, is the time required to complete one cycle. So we know that time is usually represented by small t, but if we're talking about the time required to complete one cycle or for repetitive motion, it's denoted by capital T, which stands for the period. The frequency and the period, capital T, are reciprocal of each other and can be related by. So the frequency is 1 over t, or t is 1 over f. And here let me say the following. So using dimensional analysis, because t is in seconds, so that would be 1 over second, which is second to the power minus 1, which is the hertz. So basically the hertz is given by second to the power minus 1. Now here, if you look at the following animation, so the first one has a frequency of 5 Hz, then 4 Hz, then 2 Hz, 1 Hz, 0.5 Hz. If we're reading this animation from left to right, we notice that the frequency decreases. What does the frequency represent? Is the number of cycles per second. For this, in the first one, it's doing 5 cycles in 1 second. Then it's doing 4 cycles in 1 second, 2 cycles in 1 second, 1 cycle in 1 second, and half a cycle in a second. For this reason, the speed along the circle is decreasing. And also this one requires less time in order to complete a full cycle, and as the frequency decreases, it's gonna require the moving particle more time in order to complete the cycle. Now the angular frequency omega, so remember that we have introduced the following quantities: period frequency and angular frequency. How does the angular frequency omega related to f and t? So omega is 2 pi f, which is also equal to 2 pi divided by the period, and its unit and the SI is radians per second. Then the unit of the angular frequency is given by radians per second. Now example 1, for each of the following examples, determine the speed and the magnitude of the acceleration of the moving particle s of coordinates x, y. All quantities are in the SI. Then we need to determine the speed and the magnitude of the acceleration. Here the motion occurs in a two-dimensional plane. So we have horizontal position, vertical position, then we have horizontal velocity, vertical velocity, but we need the speed, so we need to add Vx and Vy, and we're gonna add them using the Pythagorean sum, and similarly for the acceleration. Then let me start by the first one. So Vx in this case would be the derivative of this one, the constant would be 0 here. Then we can drag 4 out, and cosine 3t would give us minus sign, and this is a functional. We need to multiply by the inner derivative, that would be negative 3 sine 3t, and that would give us negative 12 sine 3t. No need to put in it because it's parameterized by time. And as for Vy, that would be 0, and we can drag 4 out. This is a functional, then its derivative is gonna be multiplied by 3 cosine 3t, and that would be 12 sine 3t, cosine 3t. Now if we're interested in the speed would be given by radical Vx square plus Vy square, which is the radical of negative 12 sine 3t to the power of 2 plus 12 cosine 3t to the power of 2. And now we can drag, or the power of 2 is for both 12 and the sine and the cosine function similarly here. Then we can factor out the 12 to the power of 2, and this square plus this square would give us 1. Then the speed in this case would be constant, which is 12 meters per second. So this is it for the speed. Now what about the acceleration? We need to derive this again. Ay would be the derivative of this. 12 is a constant can be dragged out. Cosine would give us minus sine with the inner derivative multiplied. Then that would be negative 12 multiplied by 3 sine 3t. And for Ax, let me do Ax here. Then Ax would be negative 12 can be dragged out. We multiplied by the inner derivative, which is 3 cosine 3t. that would be negative 36 cosine 3t, and that would be negative 36 sine 3t. Now the acceleration would be ax and ay combined using the Pythagorean sum. So a would be the radical of ax square plus ay square, which is the radical of ax is negative 36 cosine 3t to the power of 2 plus negative 36 sine 3t to the power of 2. Now the powers, the even power, cancel the negative sign. We can factor out 36 square, and what is inside the bracket is cosine square 3t plus sine square 3t, which is 1, and that would be 36 meters per second square. And then this is it for part 1. For part 2, we're gonna do the same, exactly the same. So Vx, let me do it quickly. Then 2r, so this is 0 and that's 0. We can drag the coefficient 2r out. Cosine would give us minus sine. 2 omega t would be multiplied out to the inner derivative, and that would be minus 4 r omega sine 2 omega t, and I hope I didn't do any mistake. So okay, now Vy would be, so we're going from sine to cosine, that would be 4 r omega cosine omega t, and here 2 omega t. As you can notice that I'm comparing both members in order to check or chase the error. Then v in this case, if we do radical vx square plus vy square, and if you factor out 4 r omega for each one, and the negative sign will cancel out with the even power, the speed would be given by 4 r omega. As for the acceleration, this is the speed, and here no need to put a unit because it's parameterized in terms of, or it's expressed in terms of other variables. Ax would be given the derivative of this, so negative 4 r omega is dragged out as a coefficient. We multiply by the inner derivative, that would be negative 8 r omega square cosine 2 omega t, and ay would be, so cosine would give us minus sine, we multiply by the inner derivative, that would be 8 r omega square sine 2 omega t, and believe me or no, the acceleration would be given by 8 r omega square, which is the coefficient of the trigonometric functions, and you can check that explicitly by doing the Pythagorean sum. Now for part 3, Vx would be given by a omega cosine omega t. Here let me state it that omega is a constant. If we're deriving 2 omega t for part 2, that would be 2 omega because a linear term gives us a constant. Here similarly, if we're deriving omega t, the linear term gives us a constant, which is omega. For this reason I'm multiplying by omega. Then Vy would be minus a omega sine omega t. Believe me or no, the speed would be given by a omega, no need to put a unit. Ax would be given by minus a omega square sine omega t. Ay would be given by minus a omega square cosine omega t, and the acceleration would be given in this case a omega square, and the minus sign would cancel with the even power. Now section 2, variables of circular motion. Variables of motion can be introduced for circular motion, and they are given by. So if we're talking about the variable of motion, we have the following list: angular position, angular velocity known as the angular frequency, and the angular acceleration. The angular position is denoted by theta, the angular velocity is denoted by omega, the angular acceleration is denoted by alpha, and the unit of theta is in radians, the unit of omega is radians per second, and the unit of the angular acceleration is given by radians per second square. The above variables of motion are understood as vector quantities, that is, they have magnitude and direction. What about the direction? The default positive direction associated with circular motion is the anti-clockwise, to be the positive direction. Then the motion of the hands of the clock is considered the clockwise direction. Anti-clockwise direction would be moving opposite to the hands of the clock, and that would be the default positive direction, while the negative direction would be the clockwise, which is the negative direction. These quantities are best understood when introduced in analogy with rectilinear motion. So we know that rectilinear motion, which is the motion along a straight line, for the position x, it is in analogy with angular position theta. So x would be replaced by theta. Velocity v would be replaced by angular velocity omega, or the angular frequency omega. The acceleration a would be the angular acceleration alpha. Now section 3, variables of circular motion. 3.1, uniform circular motion. Then remember that what we have done in the motion along a straight line, we have distinguished between two types of motion, uniform motion and uniform varied motion. In the case of uniform motion, the velocity was constant, acceleration is 0. In the uniform varied motion, the acceleration is constant and the velocity changes linearly with respect to time. Here we're gonna do the same. First, let me explain the diagram. We have a particle s moving along a circle. We have two different representations for the position. We have the polar coordinates r and theta. R is constant, theta as a function of time. X and y are the Cartesian coordinates of the particle moving along the circle. The x-axis is being generated by the unit vector I, the y-axis is being generated by the unit vector j. The title of this section is Uniform Circular Motion. So equations of motion: an object s is said to be moving in uniform circular motion if the angular velocity omega is constant, in analogy with uniform motion. That is, the object s is rotating at a constant speed and the angular acceleration alpha is 0. In this case, the equation of motion is given by theta is theta 0 plus omega t, in analogy with x is x0 plus vxt, but here omega doesn't carry any subscript because the motion occurs along a circle and not a sphere that exists in 3 dimensions. So here it's sufficient just to represent the motion via angular velocity along 1 dimension, which is omega. And the displacement in this case, if theta 0 is moved to the other side, then delta theta would be theta minus theta 0, which is omega t. Now what about the trajectory? We know that in this case the trajectory is a circle and the velocity vector is always perpendicular to the tangent to the trajectory, and v is always perpendicular to a, or let me say is a is always perpendicular to v. Now you can ask the following question: how come we have mentioned a and we've stated here that the angular acceleration alpha is 0? The acceleration a in the Cartesian coordinates has two components, ax and ay. In the polar coordinates, a has two components given by a centripetal and a tangential, or known, which is related to the angular acceleration. So the acceleration a, the total acceleration, may be due to things. May be due to the centripetal acceleration or may be due to the tangential acceleration. Now we know that velocity v has both magnitude and direction. So whenever we say that the velocity varies, it can vary in both ways, either in magnitude or in direction, or in both ways at the same time. The variation of the magnitude gives us the tangential acceleration, so this gives us at. The variation in the direction gives us a centripetal, so this is related to the variation of the magnitude of v, and this is related to the variation of the direction of v. Because the speed is constant along the circular motion, the angular velocity omega is constant, which means that s is rotating at the constant speed along the circle, so we don't have the variation in magnitudes, then that would be 0. However, now we need to check whether the direction of the velocity changes along different points. So the velocity here is gonna be like that, the velocity here is gonna be like that, tangent. So as you can notice that here the velocity is pointing left, here it's pointing down, here it's pointing right, here it's pointing up. So the direction of the velocity is changing. So we have an acceleration, and this is known as the centripetal acceleration. Centripetal because it's pointing toward the center. Then by that, whenever we have circular motion, we cannot ever avoid the acceleration because the direction of the velocity always changes. However, if we're talking about uniform circular motion, which means that the value of the speed along the circle is constant, then a tangential would be 0. We're only left with the variation of the direction of the velocity, which causes centripetal acceleration, and by that the acceleration would be always pointing toward the center and would be perpendicular to the velocity. For this reason, In uniform circular motion, I have mentioned that V is always perpendicular to A. Important remark, this is just a recap what I have said. Even if the object is rotating at a constant speed, uniform circular motion, it will be submitted to acceleration. Acceleration is due to variation in velocity, and velocity has both direction and magnitude. So along the trajectory of the circle, even if you're not slowing down or speeding up, the direction of the velocity changes, which causes this acceleration known as the centripetal acceleration. Now what about section 3.2, uniform varied circular motion? So the diagram is the same. An object is said to be in uniform varied circular motion if the angular acceleration given by alpha is constant. So here alpha is constant. In this case, the equations of motion are given by, so Vx is Vx0 plus axt, and they are both an analogy. X is given by x0 plus Vx0t plus half axt square. Vx square is Vx0 square plus 2ax x minus x0. And delta x is given by half Vx plus Vx0 multiplied by t, and the displacement, dragging theta 0 to the other side, we're gonna have the following displacement. Now here, what about the trajectory? Okay, the trajectory is a circle. The velocity always and forever would be tangent to the circle. What about the acceleration? The acceleration has two components given by ax, ay in the Cartesian coordinates. And the polar coordinates is given by a centripetal and a tangential. A centripetal is related to the change of direction of velocity, so this is always happening. What about a tangential? It is related to the angular acceleration, which has to deal with whether we're slowing up, we're speeding up or slowing down. And this is the case of uniform varied circular motion. We have angular acceleration, so the speed is changing at a constant rate. So we have a tangential, and in this case V makes with a fixed angle not equal to 90 degrees. Why so? Because if you think about it, so we're gonna have part of the acceleration which is pointing toward the center, and this is a tangential, and there is another part of the acceleration which has to deal with speeding up or slowing down. Let me say that this is speeding up, so the acceleration is upward. This is a tangent, so this is centripetal, and this is a tangential. And if you try to add both acceleration, we're gonna end up with the acceleration making an angle, a fixed angle with the velocity. Alright, so in case of uniform circular motion, the acceleration would be completely pointing toward the center. In case of uniform varied circular motion, we're gonna have both components, centripetal and tangential, and the acceleration would be making a fixed angle with V not equal to 90 degrees. Now exercise 1. In an experiment, students record the horizontal and vertical positions of an object as function of time. The students claim that the data shows the horizontal acceleration of the object is approximately 0. So they're claiming that ax is 0. And the vertical acceleration of the object has a non-zero value, so ay is different than 0. So they just said that ay is different than 0. They didn't say that ay is constant. Which of the following evidence statements best support this claim? A, the horizontal position is constant. No, we know that the horizontal position is changing. We can eliminate this. The horizontal position is changing and the vertical position is constant. We know that the vertical position is not constant. The horizontal position is changing at a constant rate. So yes, this is true. Because the horizontal position is changing at a constant rate, then the acceleration is 0. Why? Because if the acceleration is 0, the speed is constant, which means the position changes linearly, which means at a constant rate. And the vertical position is changing at a non-constant rate. So this is true. I'm gonna keep C. The horizontal and the vertical positions are both changing at a constant rate. This is wrong, because we know that if you refer to the values of the vertical positions, this is the change here is 1, the change here is 0.5. So this is a non-constant rate. The horizontal and the vertical position are both changing at non-constant rates. This is wrong, because we know that the horizontal position is changing at a constant rate, reflecting the fact that ax is 0. Now exercise 2. An object starts from rest at the origin of an xy coordinate system. Then first of all, the motion occur in 2 dimensions, x and y. From rest means with 0 initial speed both in the x and the y direction. Then vx0 would be 0 and vy0 would be 0 as well. And at the origin, it means that the initial position along the horizontal would be 0 and the vertical position along the initial vertical position would be 0, and has an acceleration of components ax and ay. Both of them are a. After t seconds, the displacement and velocity of the object are given by delta d1 and v1. Notice that here we're talking about displacement and velocity. These are vector quantities, and now they have both components x and y along. They have both x and y because the motion occurs in 2 dimensions. The object is stopped and returned to the origin. The object then starts at rest again. Okay, we're gonna start again at rest, and we suppose from the origin because it's being returned to the origin with acceleration components, then the double of the acceleration along the horizontal and the double of the acceleration along the vertical, which means we are interested in the factor of change. After t seconds, the displacement and velocity of the object are delta d2 and v2 respectively. Which of the following correctly relates delta d1 and v1 to delta d2 and v2? Then basically we need to express delta d1 and v1 in 2 dimensions, then we can apply the vector of change. Now let me represent them using the vector notation. Then delta d1 in the vector notation has both components, delta d1 along the horizontal, and let me place here a vector, plus delta d2 along the vertical, and let me here place a vector. Now remember that from the equation of motion, for an accelerated uniformly varied motion, we know that delta x is given by vx0 multiplied by t plus half axt square. Now because we are starting from rest, then this would be 0. Then the displacement along the horizontal would be given by half axt square. Then this can be written as half axt square multiplied by the unit vector I, plus similarly along the vertical that would be half ayt square multiplied by the unit vector j. Then this is the displacement in 2 dimensions. Now for the velocity v1, we know that the final velocity vx is given by the initial velocity along the horizontal, let's say for example plus axt. We're starting from rest, then that would be axt, and here we can say that v1 can be expressed as v1x plus v2y, this is v1y, which is basically a 1x multiplied, a1x multiplied by t multiplied by the unit vector I, plus a1y multiplied by t multiplied by the unit vector j. Now without doing the factor of change, this is straightforward. Why? Because what we have done is that here I can replace the 1, no need for the 1s. Now notice carefully that both the displacement and the velocity are linear in A. Then if you apply the factor of change and the factor is 2, which means that the displacement would change by a factor of 2 because it's linear in A, and the velocity also, if it's changing, if the acceleration is changing by a factor of 2 and it's linear in the acceleration, then the velocity would also change by a factor of 2. Then in this case, the correct answer would be E. The new displacement would be related to the previous displacement by a factor of 2. The new velocity would be related to the previous velocity by a factor of 2. Now exercise 3, if a particle moves in a plane so that its position is described by the functions x is a cosine omega t and y is a sine omega t, the particle is, then if we refer to the choices, we are interested in the trajectory, whether it's circular, parabolic, straight line, and we need to discuss the speed. Now first of all, because we have trigonometric functions, then we might be talking about circular motion. Now look at the coefficients, they are the same, and look at the angle, they are the same, which means that indeed we are along a circle. Then we need to test whether the speed is constant or varying. It's gonna either be A or B. Then let's check. Now Vx, which is the speed along the x direction, would be given by minus A omega sine omega t, and Vy would be given by A omega cosine omega t. And if you do the speed, which is the Pythagorean sum of Vx and Vy, that would be A omega, which is basically constant, and the correct answer in this case would be A. Now, which pair of equations can describe the path of a particle moving with zero acceleration? Zero acceleration means that the velocity is constant, which means that the position is linear both in x and in y, and the correct answer in this case is C. Now, an object is moving in the xy coordinate plane. The components of the object velocity are Vx and Vy. So they depend on time. Now, the components of the object's acceleration are given by Ax and Ay. Then also Ax and Ay depend on time. Which of the following vectors best represent the velocity and the acceleration of the object at t is equal to 2 seconds? Then let's calculate the velocity and the acceleration at t is equal to 2 seconds and choose the correct vector representation. For the velocity, Vx is always given by 5 meters per second, and Vy, if we replace time by 2, then 3 multiplied by 2 is 6 minus 6, that would be 0. No need to put a unit because anything multiplied by 0 is 0. Then in this case, the vector representation of the velocity at this particular instant would only be horizontal and positive to the right, which means like that. Then the correct answer is gonna be either D or E. Now what about the acceleration? Now Ax would be given by t, which is 2 minus 7, that would be minus 5 meter per second square, and Ay would be 4 multiplied by 2, which is 8, minus 2, that would be 6 meter per second square, which means that the acceleration is left and up, which means something like that. Then the correct choice would be E. And exercise 6 as an exit ticket for today's video. A small particle starts from rest from the origin of an xy coordinate system and travels. Now from rest means that the initial speed in the xy plane is 0, which means that Vx0 is 0 and Vy0 is basically also 0 from the origin, which means that the initial position along the horizontal and along the vertical would be 0. Its acceleration in the x direction is 2 meters per second square. Then Ax is given by 2 meters per second square, and its acceleration in the y direction is given by 1 meter per second square. What is the x coordinate of the particle when its y component? Y coordinate is 12 meters. So basically we have that y is 12 meters. From y is 12 meters we can determine the value of t. Knowing the value of t, we can determine the value of x. Now the vertical position is given by y0 plus vy0t plus half ayt square. Now this is 0, and that would be also 0 from the given, and that would be half the acceleration is given by 1, and the value of t is given by, okay, we need to determine the value of t. Now the vertical position is given by 12, then t square would be given by 24. Now let's keep it as t square because the horizontal position, it's also quadratic because the acceleration is along the x and along the y. Then both x and y would be governed by uniform varied motion. Then x is given by x0 plus Vx0 multiplied by t plus half axt square. We know that this is 0 and this is 0 based on the given and the text. That would be half the acceleration along the x direction is 2, and t square at this specific instant is given by 24, and the horizontal position is given by 24 meters. At this location of y is given to be 12 meters. Then the correct answer in this case is D. Then that's it for me in this video, guys. See you soon in a new one.